Hey everyone, and welcome to RUBIN'S Mind Lab, where we break down the latest research into what it really means. Ever wonder why it feels like your research results are sometimes a bit fuzzy, or why you get more confident in a number that might not be quite right as you collect more data? Well, this new study dives deep into that very problem. Today we're talking about correlation, that classic statistic that tells us how two things are related. Like how ice cream sales might go up when the temperature goes up. But what happens when the way we measure things isn't perfect? This paper argues that a really common way we look at correlations might be leading us astray, especially in experimental psychology. So, the big problem the researchers are highlighting is with something called the sample correlation, when we have what they call measurement error, which basically means our tools or our tests aren't perfectly accurate. The sample correlation often gets weaker than it really should be. This is called attenuation. And here is the kicker. This downplaying of the true relationship actually gets worse as you collect more and more data. That is a really strange and counterintuitive idea, right? You'd think more data would always give you a more accurate picture. Imagine you want to know how much two skills, let's call them skill A and skill B, are related in people. But you don't have a perfect way to measure skill A or skill B. You have to use tests or tasks that have some noise in them, like a slightly wobbly ruler. So you measure these wobbly versions. Let's call them measured A and measured B. The correlation you find between measured A and measured B might be weaker than the real correlation between true skill A and true skill B, and the more data you collect, the more confident you might become in this weaker, less accurate correlation. Psychologists know about this. They usually try to get around it by making sure their measurements are super reliable, meaning they're consistent and have very little noise. But what if you are working in areas where high reliability is really hard to achieve? That is where this paper steps in, offering a different approach. Instead of just trying to get more reliable measures, the researchers are proposing a way to actually model that measurement error. They use a fancy approach called hierarchical models, which can look at the variation within each person's measurements and the variation between different people all at the same time. This lets them get a better handle on the true relationship between variables, even when the measurements are a bit noisy. To explain this, let's look at an example from the paper. Imagine researchers are interested in how strong two kinds of interference are in people's thinking. They call these the Stroop effect and the flanker effect. In a perfect world, they could measure these true effects directly. Figure 1a shows what that ideal picture would look like. If you had a big effect in one, you tended to have a big effect in the other. There is a clear pattern, a strong relationship, but in reality, they can't see these perfect true effects. What they see are sample effects, which are usually figured out by averaging across many individual trials within a task. Think of it like trying to guess someone's average height by occasionally poking them with a measuring tape that sometimes wobbles. This trial noise, the small variations from one trial to the next, is like those wobbles. Figure 1b shows how these wobbles push the measured points away from the true relationship, making the dots scatter more. And when you just look at these scattered around points, as researchers often do, the pattern looks weaker. Panel C shows this. The correlation between the observed Stroop and flanker effects is much lower than the true correlation shown in panel A. This is that attenuation we talked about. The authors are really hammering this point home. The sample correlation we usually calculate is biased. It is systematically giving us a weaker estimate of the true relationship. And the really troubling part is that this bias doesn't go away just because you have a huge sample size. This is a direct quote from the paper, and it's pretty strong. They're saying that the usual sample correlation is an inconsistent estimator when there is measurement error, meaning it fails a fundamental rule of good statistics that errors should shrink as you get more data. More data means more confidence. But if the underlying calculation is flawed due to unmodeled error, that confidence is in the wrong value. They conclude that truly sample correlations should be avoided in these situations. So what is the alternative? The paper champions hierarchical models. These models are powerful because they can separate out the different sources of variation. They have two main parts, a data model and a latent model. The data model figures out how the noisy measurements are related to what the researchers call latent true scores. These latent true scores are essentially the underlying true values of what's being measured, stripped of the random trial-to-trial noise. The latent model then looks at how these true scores themselves are distributed across a group of people. This is where they can estimate the correlation between the true scores of different variables. By separating the measurement noise from the true score variation, and then looking at the correlation between those true scores, they can get an accurate, disattenuated correlation. Disattenuated just means that the upward bias from measurement error has been removed. To analyze these models, they lean towards a Bayesian approach. Now, don't let the term Bayesian scare you. Essentially, it is a way of doing statistics that allows researchers to incorporate prior knowledge or beliefs and update them with new data. It is particularly useful here because it gives them a way to measure uncertainty, the degree of wiggle room around their estimates, in a way that accounts for both the variability in the data and the uncertainty in their estimates of the measurement error itself. Figure 3 in the paper shows a great example. You see a blue histogram which represents the distribution of possible correlation values based on their model. The blue line shows their estimate, and the shaded blue area is their credible interval, which is like a confidence interval but interpreted a bit differently from a Bayesian perspective. They compare this to the standard sample correlation shown in red. Notice how the red sample correlation estimate is lower than the blue hierarchical estimate. That is the attenuation in action. And the blue credible interval is wider than the red confidence interval. This means the hierarchical model is showing more uncertainty, which makes sense because it is accounting for the complexities of measurement error. The paper emphasizes that this isn't a minor issue. When you have measurement error, those standard confidence intervals from sample correlations can be too small, meaning researchers might become overly confident in a relationship that isn't as strong as they think. Figure 2 illustrates this dramatically. The top row shows what happens without measurement error, the confidence intervals. The blue bars correctly get smaller and stay centered around the true correlation as sample size increases. The bottom row, however, shows what happens with measurement error, as the sample size increases from 20 to 100 to 500 individuals. The confidence intervals actually become less likely to contain the true correlation. This is the inconsistent estimator problem in full effect. More data, less accuracy in coverage. Pretty wild. To make this sophisticated method easier for other researchers to use, the authors have even developed a set of user-friendly R functions. They've made these freely available online. This is a big deal for speeding up the adoption of more accurate statistical practices. They tested their approach with real data. In application I, they looked at the stability of Stroop effects, essentially asking if people who showed a strong Stroop effect in one task condition also showed a strong one in another. Even though the reliability of their measures wasn't super high, their hierarchical model provided more accurate and nuanced insights into the correlation than the standard methods. In application ID, they looked at visual illusions, where the reliability of measurements is typically very high. Here, they found that the hierarchical model's results closely matched the standard sample correlations, which is what you'd expect when reliability is high. The main difference, as in the previous application, was the way uncertainty was handled. The paper also gives a warning about something many of us use: scatter plots. While useful for visualizing data, they can be misleading when there is a lot of measurement error. The scatter in the plot will be much wider than it should be, making it harder to spot real patterns or outliers. Even their model-based scatter plots, which try to show the true scores, aren't recommended because they can smooth out important details. One of the really neat capabilities of this Bayesian hierarchical approach is its ability to test how likely it is that the true correlation is a specific, theoretically important value like perfect negative correlation, 1, no correlation, 0, or perfect positive correlation, 1. They use something called Bayes factors to quantify the evidence for or against these precise values. So, to wrap it all up, the core message is this: while sample correlations are easy to calculate, they can be seriously flawed when there is measurement error. This flaw isn't just about a small inaccuracy. It can lead to researchers becoming more confident in wrong conclusions as they collect more data. The hierarchical modeling approach offers a powerful and principled way to address this by explicitly modeling measurement error. If you are averaging multiple observations to get a single score for individuals, the paper suggests you stop and consider a hierarchical model instead. The authors are making a strong call to action here. They believe this method is superior and should become the norm for assessing correlations in experimental psychology, especially given the availability of tools to make it accessible. Now, from my perspective here at RUBIN'S Mind Lab, this research is incredibly important. It tackles a fundamental issue in how we quantify relationships in psychological research. The fact that standard methods can lead to increased confidence in wrong answers as we gather more data is a really strong warning sign. The proposed hierarchical models, by accounting for measurement error directly, offer a much more robust and trustworthy way to understand associations between variables. The strength of this paper is its clear explanation of a complex statistical problem and its direct actionable solution with supporting R functions. The applications to real data, showing both low and high reliability scenarios, demonstrate the broad applicability of their method. A potential limitation, as with any statistical modeling, is the reliance on assumptions about the nature of measurement error and the distribution of the underlying true scores. While the Bayesian approach allows for exploring different prior beliefs, choosing those priors can sometimes be subjective. However, the paper addresses this by showing that their results are often not overly sensitive to prior choices. Also, the complexity of the hierarchical model might still be a barrier for some researchers, even with user-friendly functions, requiring a steeper learning curve than simply calculating a Pearson correlation. The implications of this work are significant. For researchers, it means potentially evaluating past findings that relied heavily on sample correlations in the face of known measurement error. It also provides a clearer path forward for designing studies and analyzing data in a way that yields more accurate and reliable insights. For anyone interested in psychological research, it means the findings from studies looking at relationships between variables might be more robust and trustworthy if they employ these more advanced statistical techniques. Future research could build on this by exploring the application of these hierarchical models to even more complex experimental designs and different types of outcome variables. Further development of even more intuitive software interfaces could also accelerate adoption. It's a call for greater statistical rigor in a field that relies heavily on uncovering the intricate connections between our thoughts, feelings, and behaviors. What do you think about this? Does it make sense that more data could sometimes lead you to a less accurate picture of a correlation? Let me know in the comments below. And if you found this breakdown helpful, please give this video a thumbs up, subscribe to RUBIN'S Mind Lab for more science deep dives, and hit that notification bell so you don't miss our next episode. We'll see you next time.